Hello everybody. In this video we're going to be looking at the last problem from homework 1, where we're asked to determine the expectation value of the commutator of the position and momentum operators. And they give us a psi of x and they give us bounds, but we don't actually need to use those. Atkins goes over this in Justification 7.6, where he does his own way that's a bit bare bones. And Allison specifically says, don't just use this justification. So I'm going to show you how I would solve a problem like this. And I don't need the specific psi or the specific bounds. And some equations that I used for this are the equations for the expectation value, where the expectation value happens when the operator is on one psi only and then multiplied by the other psi, or by psi again. And then I should write this is expectation value. And then it talks about commutators, so we need the definition of commutator. And this basically just means the order of the operations matter. This definition says basically the effect of these two operators applied in succession depends on their order. And if it depends on their order, then they don't commute. And basically, operators that don't commute are considered complementary observables, which in this case, we know that position and momentum are complementary observables. So here we have definition of commutator. It's a little wiggly. Hold on one second. Okay, see if that's better. And then I'm also going to write down our operators, so we have them for reference. So the operator for position is just multiply by x. The operator for momentum is multiply by h bar over I times the derivative of the wave function. So here it's saying determine the expectation value of the commutator of position and momentum. So I interpret this as I'm going to plug in the definition of commutator inside the expectation value. So I'm going to write position, comma, momentum operator equals the integral of psi star, other half of this, so we have position momentum minus momentum position psi d tau. And this distributes into the psi, so we can write this as psi star position momentum psi minus momentum position psi d tau. And Atkins shows us what these are, but I'm going to write these over here for our own reference. So we have position momentum psi equals, so we can go this way first. We can write h bar over I d wave function dx times position, so that's this, and then momentum position psi equals, we have, again, I'm going to do it right to left, to me that's easier, we have x times psi, and then we have the derivative of this, times h bar over I. And this simplifies to h bar over I psi plus x d psi over dx. And this is achieved through the product rule. So you can go through, see how that works, and make sure. Yeah. Okay, now that I have these two values, I'm just going to substitute them in. Not going to do anything else yet. So integrate. I'm just going to write psi because psi doesn't have any imaginary component. So I'm going to just get rid of that star. So position momentum times psi, we have x times h bar over I d psi over dx, this, minus momentum position psi, which we found to be this quantity. D tau. Okay. Now from here we're just going to simplify. So what I'm going to do is I'm going to pull out this h bar over I factor. So we get psi h bar over I. So we're left with x d psi over dx. Minus psi, because this goes into there, minus x d psi over dx d tau. So as we can see here, these x d psi over dx values cancel each other out, and what we're left with when we continue to simplify is integrate psi. We just pull this negative out, so we get minus h bar over I psi d tau. And because this is a constant, we can pull it out of the integral, and we can write this to mean the exact same thing as IH integral, and we're back with psi squared d tau, which is really awesome. Let me go to the next page really quick. I don't think I have enough room. Well, I'll just do this actually. Yeah, that's okay. This is really awesome because we're assuming that psi is normalized throughout this whole problem. So assuming psi is normalized, then we know from the normalization integral that the integral of psi squared d tau is 1. Because once we include that n constant, the particle has to exist somewhere. So if we're saying that, how do I say this? The expectation value of the commutator of these position and momentum operators is, we get the integral of psi squared d tau back, and this is our assumption, then it's basically as if we're multiplying both sides by IH. So this is how we know that the expectation value, or the expectation value of the commutator of these two operators is IH. Which is a pretty awesome way to come to the same conclusion that Atkins does. because this shows that position and momentum are complementary. Complementary means this, basically. When you depending on the order of operations, oh, you can't see that. Depending on the order of operations, if when you subtract these you don't get 0, that means they matter, and they don't commute, which means they're complementary, and you wind up with a really fundamental part of quantum mechanics.